Welcome once again to the next lecture series or lecture in the series of Geotechnics 254. If I'm correct, this would be lecture number 5. And many years ago, Charles E. Kellogg, and no, he's not the guy from Special K, he's a soil scientist. He said, civilization has its roots in the soil. Now, if you recall in engineering geology, we once made the statement, Professor Brink said, everything that man does is done with the earth, on the earth, or in the earth. And this is just another picture of some soil or soil works or ground works done on a site. If I look at the shape, this seems to be a catchment dam, potentially either a new water dam, or it could be for a capturing of runoff and drainage from a construction site. So as I mentioned, we will be looking at soil compaction. The lecture is in Craig, chapter 12.5. At this point, I need to point out that the new edition of the handbook has changed completely from the previous one. In the past, this would have been chapter 1.5, and the old chapter was a bit more extensive than currently. So apart from my notes, which will be very helpful for you, I really suggest that you also look at the video link that I provided, the lecture on soil compaction by Dr. Franke. It explains it in more detail, or maybe even better than I can, or at least it's a different perspective that can help you understand the concepts and the formulas, etc. and why we're doing compaction. That's the most important thing. What's the reasoning behind it? Soil compaction is the process of increasing the density of a soil by packing the particles closer together with a reduction in the volume of air, but no significant change in the volume of water in the soil. So compacting it at the current volume of water in the soil, but changing the volume of air. The higher degree of compaction you get, the higher the shear strength of the soil and the lower the compressibility. This is of course important. If you construct on a high shear strength soil, there's a less chance that the soil will shear or break, and therefore there's the lower compressibility, so there's less chance of the building settling and creating cracks, etc. The degree of soil compaction is measured in terms of the dry density, the mass of the solids only per the unit volume of soil. I repeat, the mass of the solids only per unit volume of soil. So the dry density equals the density divided 1 plus the water content. The dry density after compaction depends on the soil type. You can imagine that a soil will compact better than a gravel, but a silt will compact better than a sand. So, sorry, I repeat. A sand will compact better than a gravel, but the silt will compact better than a sand. The water content plays a very important role, because there is a point where you can have too much water and no longer will get any compaction, and the energy will be wasted. The compaction effort, or the energy supplied by the compaction equipment, is another parameter that determines the dry density. In the laboratory, we do different compaction tests, or perform different tests in order to determine the characteristics of a soil to be determined, and we are using standard laboratory tests. The soil is compacted in a cylindrical mold using standard compaction effort. So this is the big thing. You need to be able to repeat the test several times and get the same answer. There are 3 standard compaction tests that we use in South Africa. In our labs, we have all the necessary equipment, and these are all British methods. The first one is the Proctor test. I will show you pictures of the various pieces of equipment. They all work more or less on the same principle. In the Proctor test, the volume of the form is 1 liter. It has a rammer with 2.5 kilograms of mass, and you lift up the hammer and let it fall, free fall 300 millimeters. And you build up 3 equal layers, of which there are 27 blows in each. So the hammer falls 27 times. That's essentially what it means. The modified Ashto, or commonly referred to as mod Ashto, the volume of the form is still 1 liter. It's the same as the previous one. But now we have a rammer with 4.5 kilograms of mass. The free fall distance is 450 millimeters, and we compact 5 layers, each with 27 blows. Then the vibrating hammer has a form of 2.3 liter. It is a circular tamper fitted with a vibrating hammer. We compact in 3 layers, and each layer is compacted for 60 seconds. On the left, this is what the Proctor equipment looks like, and then on the right is the mod Ashto. It's slightly bigger, slightly heavier hammer that falls over a longer distance, but it's the same mold that is used, or form. And the vibrating hammer uses a different form, which is still circular, and this is what it looks like. And this piece of equipment has just been moved to the new lab that was constructed recently. So in the first cycle, when you do soil compaction, this is the first level cycle. So blows number 1, 2, 3, and 4 is done in this way, and then 7 or 4, 5, 6, 7 till 27 is done in this way around the outer edge of the form. And then depending on which method we use, we are using 3 layers or 5 layers or more, depending on which equipment we use. This compaction process is repeated at least 5 times per soil sample with increasing water content. So you repeat it 5 times and you add a bit more water every time. From this test, we can determine the water content and bulk density. And then from that, we can determine the dry density. And the dry density is then plotted against the water content. And in the end, you can get the optimum dry density. What is the maximum density that you will ever achieve? So the optimum water content or moisture content, this W opt, is the water content at which a maximum value of dry density is obtained for a specific compaction effort. Different methods will give you different answers, and so often the person who wants the test done will have to specify which kind of test you want done and at what compaction effort, and also percentage of maximum. Then the zero air voids dry density, ZAVDD. This is the maximum possible value of dry density. So all air in the soil is expelled by compaction. But in practice, this is not feasible. But above this zero air voids dry density is represented by PD0 equals the specific gravity divided by 1 plus the water content and specific gravity times the density of water. The dry density after compaction at a water content W to an air content A is calculated as PD, dry density, equals the specific gravity 1 minus the air content divided by 1 plus the water content times specific gravity times the density of water. And once you've done all the tests, then you can plot these lines of optimums, and this is a very typical thing. So high compaction effort, you get the top curve, and then medium and low, and then you draw this line of optimums, and from that we can determine the optimum dry density. The different soil types, moistures and density produce different results. So the top one is a well-graded sand, then a clay with high plasticity, and a poorly graded sand. In situ compaction, the what we're saying here, this is the compaction we're doing while we're in the field. So what you see while you're driving along the roads and construction sites and road works, for instance, the work that Martin and East has been doing for ages near the Somerset West Mall, you probably have seen a lot of these compaction instruments or machines. And the reason why we have to look at it is because the laboratory compaction results is not directly applicable to field compaction. Because you get different compaction effort and it's applied in a different way. And the main thing is that we have to remember the lab compaction is only done on particles smaller than 20 millimeter or 37.5 millimeter. Whereas in the field or on site, these particle sizes can be bigger. If you work with gravel, then the gravel is at the upper range of this size. The maximum dry density obtained in the lab using a 2.5 or 4.5 kilogram rammer covers a range of dry densities normally produced by field compaction equipment. So these methods, the Proctor and Mott Oster, had specifically been developed to mimic what happens in the field. In situ compaction, you have to provide the minimum number of passes of the machine with the compaction equipment to produce the required value of dry density. You want a certain value of dry density, which you have calculated to be safe for the type of construction that you're doing. And the number of passes is based on the type and the mass of equipment, as well as the thickness of the layer that you're trying to compact. Roads, for instance, are very typically built in 150 millimeter layers. So if you know the thickness of the layer, what piece of equipment you're going to use, depending on what layer we're dealing with in the road, you can have as little as 3 to 12 passes of the equipment. The thicker the soil layer, of course, the heavier equipment to produce an adequate degree of compaction. Then we apply two approaches to achieve the satisfactory standard of compaction. First of all, the method compaction, and then the end product compaction. The method compaction prescribes what type and mass of equipment to use, what is the layer thickness to be, and the number of passes specified. So it needs to be specified to the contractor what machine he's going to use, how thick the layer needs to be that it works on, and how many passes the machine needs to go over the same product, same area. Where the end product compaction, the required density is specified. So the dry density must be equal to or greater than a stated percentage of maximum dry density obtained in a standard laboratory compaction test. So what this means is essentially, typically if you do Mott Oster, which is very common for use on roads, you will say to the contractor, I need the compaction to be 96% of the Mott Oster value. You cannot get 100%, so you often have to state, and it's often 96 or 98% of Mott Oster, and this can be tested in situ by various other methods to determine if you actually do have the required dry density and level of compaction required. The types of compaction equipment is described on pages 559 to 562, but I'm going to show you some pictures now, and you've seen most of these probably. And in the previous version of the handbook, there was a performance of a range of standard soils with different types of compaction equipment, but it's not as detailed in the new handbook anymore. So, kind of machines, first of all, the smooth drum roller, and this has a smooth drum with a weight inside, and often this drum also vibrates to give a certain compaction effort. Then the pneumatic tired roller, you must have seen this especially on asphalt roads, where the tires are inflated to a certain pressure, and this is then used often in combination with a smooth roller. On gravel roads or at the lower levels of road construction, they often use this so-called sheep foot roller. And sometimes the sheep foot is more prominent than even in this case, where you literally have a small pad on a short stem that literally looks, that's why it's called the sheep's foot roller. And then the grid roller is another way of compacting loose material. And then often when they do road repairs, you would see them using road rammers in small spaces or on potholes. And then the vibrating plate as well on repair of potholes. And the vibrating plate is also often used for compaction of paving. Thank you very much.